Hello, this is Dr. Peter Gorham, and you're watching the Break It Down Show.
This is fun, man. I love doing these things. You're in Hawaii. My cousin who's joining us is in Missoula, Montana area, and I'm here in Orange County, and we're going to talk about neutrinos and stuff that's going to blow my mind. We've had a lot of people come on and talk about, we tended to talk to cosmologists a lot and folks who study the big unknown. And one of them is Dr. Andrew Friedman, who works at UCSD. And he blew my mind because I was talking and I reasoned my way into, hey, wait, there must be quantum gravity. And he's like, yes, we have no idea what it is.
That's right.
So we get to these edges of my comprehension of science, and I love doing that for the audience and everybody else. So one, thanks for coming on the show. And then also, it's my cousin, Alex. He is studying physics, and he's like very particular about how I say it. So he's about to graduate with a degree in physics, and he understands a lot of what you guys are doing. So he's going to help me ask some good scientific-based questions. But thanks for coming on the show. Alex, tell us about Peter and what you found out.
So Peter is head of the, sorry, I have trouble with abbreviations, but it's the Antarctic, oh my goodness.
Impulsive
transient antenna.
That's right.
Sorry about that. Yeah, you guys are trying to find neutrinos that are shooting through the ice, and you have this whole compounded group of antennas, like a large number of them, that are basically floating above Antarctica like a balloon.
That's right.
Yeah.
Well, in fact, a balloon is what does the floating part for us. So NASA has a program that has been running for decades where they will loft scientific instruments up into the stratosphere. And we took advantage of that opportunity, which takes place in Antarctica. During the summer in Antarctica, you can go up in a balloon and circle the pole in what's called the polar vortex. So we're kind of familiar with that idea of a polar vortex here in the US because it makes very stormy weather in the Midwest up through the East Coast. But in Antarctica, that creates actually very beautiful, stable weather during the austral summer. And in the stratosphere, it creates literally a circular flow of wind. And we can fly a balloon up to the stratosphere 20 odd miles up and just circle the pole for up to 2 months. So it gives us opportunity to put something up into near space at a very tiny fraction of the cost it would be to do a spacecraft.
That's awesome. So
I finally got my marquee up here. That took a minute to kind of drop one of your letters.
So how much time do you guys spend out there when you're performing this?
So we usually go out in the beginning of November. Sometimes guys will come near the end of October. So that's the very early part of not quite summer, I guess. That's late spring in Antarctica, in terms of seasons at least. And then it takes us about a month to get our payload ready because we've had to break everything into little pieces and ship it in containers, and then fly it on C-130 type transport aircraft down to the ice. They land on the ice with skis. They outfit these military aircraft with skis, and they land on airfields made out on the ice. And we get all that stuff and into some payload bays that are set up also on skis out on the ice shelf itself, the Ross ice shelf, which is floating on the Ross Sea, but it's near McMurdo Island, or Ross Island, which has the McMurdo station on it. So, the best comparison I could think of is this is like a big mining camp, except it's in Antarctica. And, the weather during that time of the year in McMurdo is actually not so bad. It's kind of ski resort temperatures, I would say. Much nicer than working at South Pole. And the difference is when we launch from there, since we're already offset in latitude from the South Pole, we're going to circle on a much wider circle around the Antarctic continent. But after about a month of getting ready, then we get into the launch season, which starts in early December. And if we're lucky, we launch in that first week or two of December, and then we could fly for up to a month and a half, sometimes even 2 months if we're very lucky.
I love the logistics that it takes to get to places like Antarctica. To me, it's just fascinating. Like, as a military guy, I want to ask, like, okay, so you've got a grant, and let's say they give you $250,000. I would assume that doesn't cover the budget to get all of you to the South Pole. I mean, it's got to be very expensive, and you have to task out Air Force Air. Maybe they do something because it's part of a research grant, but getting C-130s outfitted with skis to the South Pole. Okay, one, how long does that take? How rough is that on your equipment? How much does that cost in terms of time and dollars as well?
I honestly don't know how much those individual flights cost, but the fuel alone is very costly, and you've got a full entourage of the, I think it's the Air National Guard that flies our aircraft.
Okay.
And these guys are absolute professionals. They're the best of the best. Without them, we couldn't do the science that we do. So, hats off completely to these personnel that run all this, the pilots, the support crew. The whole operation in Antarctica is a tribute to what we do in America. One of the things we do best is science. And, the National Science Foundation organizes this whole thing. It's run out of what's called the United States Antarctic Program, USAP. They coordinate everything. And I think I heard at one time, this was maybe 10 or 15 years ago, that if you did a full cost accounting on what it costs to get somebody to the ice and back, it's about $50,000 a head. So that's, and actually, if you go as a tourist to Antarctica, you can pay that much to get yourself onto the continent as well. So it's probably not too far off the mark. I think as a scientist, we're privileged to have that opportunity, that the American people are willing to support this kind of science is, a really amazing thing. Students, we bring graduate students down, young professionals early in their careers, and it's just an unbelievable experience for everybody. And the science we can do down there is unlike anything on Earth. So, hopefully that'll encourage us. We're all paying taxes to make these kind of things happen, but some of our tax money is doing really incredible stuff.
So I was reading that you and some other members of your crew had become sick during some of your experiments there. Could you talk a little bit about that, and how difficult does that make things when you're in such a remote area and you're trying to get a job done?
Yeah, there's a long history of what we call the crud. I guess the McMurdo crud is what they usually call it. I think if you're a military guy, Pete, you're probably familiar with this. Any little closed group in a camp situation, you end up with viruses that circulate, and that's as bad as any place on Earth in Antarctica, where you really have a closed society. We're all eating together. We're all in the same mess, and in addition, because of the environment, I think it accentuates and heightens the virility of some of the bugs that you get down there. It is a microcosm of society, and there was when I went in 2016, I'm used to getting sick at least once. You're always out for a few days with flu-like symptoms. And that kind of runs its course through the whole population down there. But in 2016, 3 days after I got down there, I felt something coming on. And at first I thought, well, here it comes. I got the crud early this year. But within a few hours, I was on my back in their little hospital. It's a small operation with, I think, 3 doctors and several nurses, and with 103, 104 degree fever. And I've never been that sick. And they were trying to pin it down at the time. They're in the rest of the world, Ebola was the big worry. And so the first question everybody was asking me is, have you been to Africa lately or something like that? But, it was really difficult. My chief engineer came in at one point and said, I was the palest looking, not dead person he had ever seen. after just one night, they decided they didn't want me to die on their watch, and so they put me on a C-17 back to, I think myself and one or two other people were the only people on that aircraft, and sent us back to New Zealand. And in the care of the doctors there, I got better in about a week, but they never did isolate what the virus was that put me down. So
that's the other thing about when you go to these places, the environment is so different. Like every time I would deploy to, say, Iraq, when I got there, I was going to basically have like a severe allergy reaction, which sounds worse than it was. Sometimes it was worse than other times, but you get hit with all this stuff you're just never hit with. And like the theory that a virus would just die out if it's left alone. There are not that many people in Antarctica, it turns out. But when you go to these foreign places, you really can get hit with something that your body's just not ready for at all. It's crazy.
That's right.
And then the other thing is it's game time. You guys are spending $1 bazillion to get there. You don't want someone around you who's sick, but you're not going to avoid it. So how do you, as the leader, go, hey, go to bed and quarantine for 96 hours, or do you just say, hey, we're all here to work. If you can work, I expect you to.
I think with the sort of history of people having this kind of relatively mild illness, we sort of leave it up to everybody to make their choice and try to do the best you can. I think within the last few months, though, the world has changed in how we think about disease, hasn't it? So I don't know, I don't know how that's going to affect anything like this in the future. I think, we've sort of turned the corner on something quite different. But as scientists, we're down there to do a job. They a lot of times, to keep morale up, they'll offer trips to some of the outlying, sites and scenes within the McMurdo area. But very often as scientists, we are so focused on doing that job that we're the last ones that jump on these little boondoggles to go out and, see Scott's Hut or Shackleton's place that he started his expedition. Those places are incredible sites, but when you're there in Antarctica and you have this limited time, you really feel the responsibility of trying to do the best job you can for the people that are counting on you, and it really is exciting. McMurdo is set up as a station where science is number one. It's probably one of the few places in the world where the most important activity there is, it's not defense, it's not making money, it's it's purely to get the best possible science that we can do. And so as scientists, we feel that responsibility, and we want to do that job. It heightens it for us, and it really is incredible. It's a beautiful place, though. If you ever get an opportunity, absolutely take it. I've never been in any environment like that. It's so pure. Even bacteria, and unless you bring a bug with you, there's nothing there that's going to get you. I mean, maybe there's some aliens or something that we haven't discovered, but for the most part, it's just an incredible, pristine, pure environment, and really ideal for the kinds of things that we were trying to do.
So I had a misconception about neutrinos, and I was learning more and more about them this last semester under Dr. Bolman, Alexander Bolman. He was teaching me quantum physics 1 and 2. I was under the impression that neutrinos didn't really have too much trouble traveling through something like a planet. Could you school me on why I was wrong about that?
Well, so you're not wrong about that, actually. But neutrinos, like every other particle, come in, so there are kind of 6 varieties of neutrinos. 3 that we know of. We call this in physics, we call it their flavor. It's a funny term that we use just to distinguish the type of neutrinos. But just like we have charged particles, the electron, we have some cousins of charged particles that are unstable called the muon and the tauon. We also have 3 neutrinos that correspond to these so-called leptons. So those are we call them leptons because they're very specifically these sort of tiny charged particles. Neutrinos kind of share these families. And then they also have antiparticles, which we don't know yet whether neutrinos have identical antiparticles or antiparticles that are true opposites of them. That's something that we don't know. But with these 6 different kinds of particles, there's one other degree of freedom, and that is how fast they're going. So if I take a lead bullet and I throw it at you, gently, and it hits you in the forehead, you don't die. You might be annoyed at me, but if I put that in a gun, then we have a major crime going on, right? And the same thing goes with neutrinos. That bullet, a bullet can be fired with an energy, but really what we're saying is that the bullet itself, which contains many billions upon billions of atoms, the energy per atom, even when you fire the bullet, is actually very small. But in the case of neutrinos, we can have a range of energies that goes from the tiniest possible energy neutrino all the way up to neutrino energies where a single neutrino has the energy of that bullet. Even though it's only one subatomic particle, it can have the energy of a bullet or a major league fastball or whatever you want to think of. And the difference now is when that neutrino with this very, very high kinetic energy, when it goes through a material like solid rock, it's much more likely due to its energy to hit something. In effect, what happens is it looks bigger than it does when it's got very low energy. So you can think of it as being neutrinos at low energy, which are the vast majority of all neutrinos, the ones that come from the sun, the ones that are left over after the Big Bang. All of those are relatively low kinetic energy neutrinos. Those are going to pass through, a planet. The lowest energy ones are going to go through 10 light years of lead and never stop. And so what I tell my students is those neutrinos are as much smaller than a proton as a proton is smaller than the entire Earth. Okay, they're so tiny that they just fit between everything. It's kind of like acupuncture, right? You can make a needle so small that it goes right through between the cells of your body without doing any damage. And the same thing is true for neutrinos. They can be so incredibly small that the universe to them is all empty space, including your body, the planet, the 10 light years of lead, whatever, But when you increase their kinetic energy, they become in some way larger. And it's hard to explain, but that's probably the simplest way to think about it. Even when their kinetic energy is as much as that major league fastball, they're still going to pass through a lot of material, maybe 100 kilometers of rock before they hit something. And no other particle even comes close to that. I mean, you can shoot X-rays into matter, but they're going to stop in maybe a meter or something or less. You shoot them; they stop in a piece of metal in your tooth. Okay, and so it's the case that neutrinos have this unbelievable property of being so penetrating compared to every other particle. But even within their own range, there is a huge variation on what they can actually penetrate through. So in our case, we're looking for neutrinos which are much easier to stop than the ones that come from the sun or that come from the earliest parts of the universe. And the reason we're doing that is we're kind of interested in what's happening in the highest energy particle accelerators in the whole universe. Those are things in the centers of very active galaxies, quasars, black holes, things that are unbelievable environments that our Earth would be vaporized in an instant if we were anywhere near it. Those things exist in the universe, and we see them all the time. These are environments that that are unlike anything, even in our own galaxy. Our galaxy is a relatively benign place compared to some. Some galaxies, you couldn't have planets like we have exist in them. They're so full of energy and radiation and particles moving at these vast kinetic energies. We would never survive there. What are those kinds of environments like? What particles do they produce? What kinds of things can we use to probe them? So neutrinos give us that opportunity. They're almost like a flashlight that can look down into these incredibly hot environments in the cosmos where everything else seems to be, impenetrable, I guess you would say. That was our goal with ANITA, was let's try to see if we can see particles that originate in the highest energy accelerators in the whole universe. These are things that are 1 billion times more higher energy than the best we can do at the particle colliders we have on Earth, like the CERN Large Hadron Collider, any of those kind of colliders. So that got us excited, and we proposed this to NASA quite a long time ago, and we were able to convince them that this was an opportunity that would allow us to do that. The reason was the ice. The ice is what makes the difference for us. So you can ask me why.
Before we ask you about the ice, I don't want to get past some of the size of what you're doing. You're talking about particles that can fly through anything before they even hit anything because they're so small and they're different levels of energy charge. But you're also measuring things in picoseconds,
yes,
which are, I don't know, by my count, like a quintillionth of a second or something like that.
Well, that actually pico is a part in a trillion. But there are people who even go down to quintillionths, which are they call them attoseconds.
Attoseconds.
Yes. Wow. So that's we're nowhere near the record on what can be measured in that sort of time domain. But yes, part of what we have to do is measure things down at the, I would say maybe the 5 to 10 picosecond level or thereabouts, just to make sure that we preserve the accurate phase of everything that we measure. When we measure a radio wave, we want to know exactly where we are in the the crests and troughs of that radio wave. And since the radio waves themselves are coming by and they're up and done in a nanosecond, if we want to measure things accurately, to a percent level, we've got to measure down to kind of 10 picoseconds to accomplish that.
Wow.
So you mentioned the ice, and is it just because Antarctica is just one great white spot that we can somehow use to sort of like an antenna, for example, to locate these?
That's a pretty good analogy. It's a little different in neutrino physics. We have never found a way to focus neutrinos. Theorists have maybe come up with some harebrained ideas on what might work, but they won't focus like you could focus in a lens or telescope. So even the way an antenna works, which is you can use the radio waves to accelerate electrons in a metal, that doesn't work with neutrinos either. So the only hope we have is they just crash into something, and the thing they crash into makes a little squawk of some kind. In our case, an electromagnetic squawk. And we managed to pick that up with our antennas, which are listening to the ice for those radio squawks if a neutrino happens to crash into something. And in more detail, it's when the neutrinos that we're looking at, so we measure energy in particles in a funny way. We measure it according to how many volts it would take to make an electron go as fast or have as much energy as that particle. And we call that electron volts. So, it's kind of a fairly simple idea. You can think of it as just in terms of volts. So a lightning bolt has, something like, as many millions of volts. The particles that we're looking at, the neutrinos, have about 1 billion times 1 billion volts of energy individually. So when they crash into a nucleus, that 1 billion times 1 billion volts can actually, by its energy, can create a whole new secondary zoo of very energetic particles, more like the ones we're familiar with, electrons and other things like that, and gamma rays. And those will make a thing that's like a lightning bolt with 1 billion volts, but it happens inside of the ice. So you think of a solid material. If somehow you could be in that material maybe in a hollowed out sphere of glass or something, and you're sitting there, and one of these neutrinos crashes into a nucleus nearby, you're going to see a flash of lightning, maybe 20 or 30 feet long, through the ice. It'll be that bright, and that crack of lightning in the ice actually makes a big spark, if you will, and it makes a big static sort of radio wave, a crack of static, just like you would hear if you're out in the Midwest driving with your AM radio on near a thunderstorm. You're going to hear, every time the lightning goes, you hear a crack on the radio station. That's exactly the kind of thing we're listening for as we fly above the ice. So the idea is very simple. Of course, all the devil is in all the details. But one thing that ice does for us is it provides a material that's solid. So, it's easier to have the neutrino hit something, but it's also extremely clear to radio waves. Much more clear than any of our ideas for clarity, okay? We're used to glass being clear, right? Glass is maybe a quarter of an inch thick, and it's completely clear. But if you make glass, 10 feet thick, it's not clear anymore, right? It gets very dark. If you've ever seen a bunch of glass, together, it gets dark, and 10 or 20 feet of glass, you won't see anything anymore. Ice is very different. In the radio regime, if you have a mile of ice, you could see right through it if your eyes could see radio waves. It's completely clear. And scientists have been using this property for many years to map the subcontinent in Antarctica by using radar. They just bounce radar off the bottom and it comes back, and they can make an image of what's going on underneath the ice. So if you could fly over Antarctica and you had radio eyes, you would see right down beneath it. You would see all the mountains and valleys and lakes and everything else that's underneath. So that's the other wonderful property of ice, is it's extremely clear to radio waves. There's nothing like it on Earth. Even the clearest water doesn't compare to this. There's no solid material that we have anything to compare it to. There's nothing like it. Ice is a miracle to me. We've heard a lot of wonderful things about ice, and there's 19 different forms of ice, all those kinds of crazy things. But this other property of ice is not one that that's well known outside of the scientific community. It's utterly clear to the radio regime.
So there was another project that was, was working on finding events in the ice in Antarctica as well. Was there not? Yes, IceCube.
It's called IceCube. The IceCube name comes from the fact that they've instrumented a cubic kilometer of ice at the South Pole, and they've put very sensitive optical light detectors into the ice. Deep down, maybe 2 kilometers deep in the ice, and they're looking for neutrinos as well. So they're actually, what I said about this lightning bolt, if the neutrino hits something and makes this blast of secondary particles, IceCube sees that as well in the optical regime. And ice is also very clear optically as well as to radio. It's maybe 10 times more clear in radio, but it's still quite good optically. So, maybe 100 meters of ice is equivalent to 1,000 meters of ice. 100 meters optically would compare to 1,000 meters in radio. But that's still very, very good. There's no other material optically that clear as well. So IceCube has used that property to look for neutrinos at lower energies than ANITA. They're looking at energies which are about 1,000 times less than what we're looking at. So the neutrinos they're interested in are still 1,000,000 billion times the voltage of a 1 volt battery. But it is a different regime of neutrino energy, and they've started to actually see some significant events, whereas ANITA is still setting upper limits on these kind of events. We haven't quite gotten enough sensitivity yet. But IceCube is starting to open that window. Anita has seen some strange things, though, that we can't quite explain. So that's gotten us some interest among the wider community in trying to understand if we're seeing some new type of physics or just something anomalous about the way we're looking at things in Antarctica.
Yeah,
and
how
you're
do
saying
you?
that.
Oh,
Sorry.
let me ask something real quick. How do you sort out the noise? We're a noisy planet because we like energy to communicate and to entertain. And is that a problem down there? I mean, is that why you go there? How does that work?
Well, it is why we go there. We go there for the ice. We also go there because it is one of the radio quietest places on Earth, but it's still got a lot of radio noise. I mean, when we first launch above McMurdo, we can't do any science until McMurdo goes over the horizon, because even that relatively small mining camp, if you will, has still got far more radio noise than we can tolerate. But once we get over the horizon, then things get pretty quiet, and we can tolerate the other kinds of noise that we do see. We see satellites. We occasionally see field camps of other scientists, but for the most part, it's tolerable, and we just have to kind of sift our way through the data in order to exclude the stuff that's produced by human activity.
And it's the same in astronomy too. All kinds of air pollution that we have to deal with when we're, just collecting data from the skies.
Yes, and in fact, some satellites have gone up that are making that even harder for astronomers, I believe. The more satellites you get in the sky, the more contamination of dark star fields you get. So, this is a problem we're going to be facing. For the rest of time, I guess, for science. There's always some conflict between human activity and the sort of quiet we need for science to do its best.
What are we going to do with all this information? Like, what do you have any idea how this will be applicable? Is someone else using your science to advance their science? What are the secondary benefits, and what are the I think these things might be kind of happening thoughts.
Well, so that's always a good question, one of the things that we've done in American science is early on, I think scientists made this distinction between what we call basic science, basic research, and applied science. So basic research is that kind of investigation, that realm of research in which we don't actually know what the immediate benefit is going to be. And then, on the other end of the spectrum is applied physics or applied research, where we know exactly what we want to do. We want to produce a better can opener, or something like that. So those are two ends of the spectrum of science. And, there's an enormous range in between. And often what happens is something that starts as basic research over the course of time becomes applied physics or applied science. So a good example, is, in the 1890s, Pierre Curie put some radium in his drawer, and he happened to put it on top of a photographic plate, and discovered sometime later that the photographic plate had gotten exposed by the radium, because the radium, in fact, was radioactive. And now we know about radioactivity. It was making X-rays, which actually went through the cover that was on his photographic plate and exposed the film. Well, that was a novelty early on. Right. People played with radium. They didn't realize what they were up against. But it took about a generation for that to become the most important tool in medicine in the 20th century, probably, X-rays. We still rely on X-rays to this day for almost everything we do in medical and dental science. So that took about a generation for that basic research to become applied science. With neutrinos, I have no idea where it's going to go. We're in a universe of neutrinos. They're among the most numerous particles, or that we see anywhere. We're bathed in a sea of them. Every moment we're speaking, 1 trillion of them go through the tip of our noses, and yet we know so little about these particles. And so I think that in the case of neutrinos, I cannot tell you if it's going to be a generation before we see the applications, or 2 generations, or what, or if we ever do. But it could be something that changes everything. We don't know. There are these if physicists were not working on quantum mechanics back in the 1920s and 1930s, we would not have a transistor in the 1960s. And if we didn't have a transistor in the 60s, we wouldn't be doing what we're doing right now, right? We wouldn't have a cell phone. Among the most absurd things that you could have told someone in the 50s or 60s is that they would have a little tiny box that they could carry with them, talk to people with, on the other side of the world, and could also listen to music with. I mean, people would have thought you were completely nuts, and yet all of
and
that.
Not just listen to music, any song, any piece of music ever recorded.
That's right.
Any way it has been recorded, any version. Yeah.
And that all came out of Bell Labs, people playing with pieces of silicon and saying, "Hey, look at this thing! Look what I can do with this! Isn't that cool?" So all I can do is plead no contest. I don't know where neutrinos are going to get us, but it could be something wonderful. And I think we, as Americans, this is something that we have done as good as anybody in the world, if not better than anybody in the world for generations now. We've chosen to invest in basic research, and I think we better keep doing it because we just don't know. If we hadn't done it in the past, we would not be where we are today. So it is, I don't know, there's something exciting about this universe of particles that we can barely understand and barely feel. You may have heard some things about parallel universes. Well, this is not the kind of parallel universe that people, were attributing to Anita, but neutrinos in their own right, they almost constitute a parallel universe, but it isn't parallel. It really is part of our universe, and it's one that we barely know anything about. So
that's a great example too of how people from the outside looking into the world of science often misread something or misinterpret something that's being told. And like, how often in your own work have you had to deal with that, where you've said something and maybe it's not really been construed correctly by whoever you were saying it to?
I can't say that any journalist has ever gotten it exactly right. And I think that's perfectly fine. That's, in the end, God made this universe. Somehow or other, I'm trying, myself and many other physicists are trying to figure it out. And we've no doubt interpreted it in some goofy way. And it must give, it must make God laugh continuously the way we interpret his universe. In the same way, I've tried to explain things to journalists, and because of my inability to do so, they can completely get it wrong. But I think what journalism does is it captures the wonder of what we're doing, and that's the most important thing. The universe, without making anything up, is incredible and wonderful and amazing. And so, however we communicate it, as long as we do our best to try to stick to what we think is true, I think it's all good. I really have no beef with any of this. Sometimes it gets me in trouble. The story about parallel universes went back to NASA, and NASA got a little bit huffy about whether I was telling people that we had discovered a parallel universe, which was not quite true. But once we sort that out, everything is good. I think it's we're all trying to make sense out of something which is almost incredible. The universe we live in is incredible. It's we're barely able to scratch the surface in understanding it. And I'm very happy that we get the opportunity to do this as scientists. And part of our job is to try to communicate to the best we can to the people that are actually supporting this. it's just a privilege that it humbles me to think about the privilege that I have to be able to do this kind of thing.
When I think about people that have done this kind of work, generations ago, someone like Faraday comes to mind, where he only barely gets to do what he wants to do. And once he gets there, oh my gosh, he changes the entire world. Are we better at finding the Faradays now? Like let's say that you're on a peer with his in terms of his brilliance and everything else. Do we find more of you out there that can go out and change how we see and how we use the world? Because his inventions, the generator largely works the same way as he described 200 years ago,
Yeah, it always amazes me. I consider myself at the very bottom of that, of that fraternity of people. I'm honored to be able to call myself a physicist in the same profession as some of these other guys. These guys are, they're bright lights in the history of science. I don't know, how do we find these guys? What scares me sometimes more is how many future Faradays and Einsteins and Mozarts have died because we, as humanity, haven't been able to, have more egalitarian communities and distribution of food and distribution of medicine. And as the human race, we don't know what it takes to make these incredible geniuses. But I guarantee you, we've probably missed out on more than we have found because of the inequalities in our societies. So that part, I think, is saddening, but at the same time, it's just amazing and wonderful when you see these guys who make these kind of breakthroughs: the Einsteins, the Faradays, the Maxwells, the Dirac's. It's just it's humbling and wonderful to be a part of that.
You think about someone like Philo Farnsworth, who's choked out by legal things and the pursuit of money. And what if someone had just funded him and let him, or even Tesla? These guys don't always make sense in the real world.
That's right.
My goodness, incredible what their brain can come up with.
I think, as a society, we're the ones that have enabled a lot of this because of the generosity to science and the investment. And I just hope that we can stick with it, that we don't forget that, very often the payoff is going to be for our children or our children's children. And, let's hope that even in these tough times, we can continue to keep that as a priority.
What do you think makes a scientist? Just is it the ability to look at the world and observe it and follow the scientific process? Is it how much you research something? Is it what you do in your life? All the above?
I think it's curiosity and tenacity and not letting it go. Giving your passion the chance to really guide you, and you have to couple that with some hard work. There are certainly people in my profession who have extraordinary abilities and skills and mathematics and understanding, which I don't think I really had. I remember getting excited about physics long before I discovered how hard it was, and I think that excitement carried me through the hard parts. I'm still learning. I will teach a class in undergraduate physics and learn something that I thought I knew all over again. And so that kind of excitement about learning, curiosity, never letting go of that idea, even when it seems impenetrable and inaccessible. You have to be tenacious about going for knowledge. Knowledge is, it's a precious commodity. The truth is a precious commodity, and you have to be committed to the truth. You have to have a burning passion and love for what's true and what's not. I think that's what makes a real scientist.
When I talked to Dr. Friedman, he talks about their work trying to prove or disprove the Bell test, and they do the cosmic Bell test. And when they talk about the parameters of their experiment, you have to give up certain things like freedom of choice and these things that aren't surrenderable in our defined world, you know. And I know you know about what I'm talking about with this, but do you have things like that where, like, if these things are true, then this absolute truth can no longer be absolutely true?
Well, you know, one of the things that you go into when you're trying to work on some hypotheses is we're human, okay? We have our likes and our dislikes. There are hypotheses when we first come upon them, we like them. We like them better than other ones. And what makes the difference, I think, in science is even if you have a bias toward one thing, you have to somehow, you know, step back and say, all right, whatever the outcome is of this experiment, even if I end up in a place that didn't prove my favorite hypothesis, that proved it wrong, for example, and makes me look bad because I invested too much in that. Well, I have to be ready for that. And, you know, that I think is the mark of that's a kind of humility that we all have to have in seeking the truth, is sometimes it ain't what you thought it was. So, you know, we have to love the truth more than we love our own, sort of self-interest. I think that's really, really important. And his experiment, by the way, was incredible, and you know, I feel humbled by that. You know, even considering what we've done. You know, I like sort of taking the machete through the tall grass, and what he's talking about is using tweezers, you know, in effect on very, very minute effects. And you know, I sometimes feel like I'm not sure I would have the patience to go through and measure things at that level. It really is a remarkable experiment what he did in that measuring that cosmic Bell's inequality. So hats off to those guys. Yeah.
And just explaining it breaks your brain. Like, you're like, wait, what? I don't have freedom of choice. I don't, you know, I have to give up these things. It's just, and then the data they have that they gathered from this is massive. So they can go through and they can write papers the rest of their life on the data that they've gathered from this experiment. It's incredible what you all are thinking of and coming up with. And shoot, if nothing else, I thank you guys for taking the time and effort to go have a blast, but go do all that stuff, you know?
Sometimes pushing it to the limit, though, where I don't think I'd want to go through that hospital in McMurdo experience again. I'm going to try to avoid that in the future. But you know, those are the risks that we take, and you know, it's we're in a world, I think, that's shrinking in many ways, but by the same token, there are ways that we can expand the world by looking more carefully and more deeply and more methodically into these areas of investigation, whether it's on the smallest scale, you know, just trying to understand how this virus has affected us. If I had to start over, I think the idea of going into molecular genetics, absolutely fascinating. So, you know, if you have a chance, get a molecular geneticist on your program. I think that is really, it's so incredible. The tools, you know, a lot of tools that just didn't exist at the time that I started in science now came out of actually physics. I think, you know, physics has contributed many of these things, but now it's become the hallmarks of biology and molecular biology and genetics. Some really incredible work that's being done. So,
what do you think's on the horizon for projects that are looking for neutrinos? Do you think that there's going to be some other location, fancy location somewhere inside the Earth, maybe, where they're going to be searching for these things?
You know, at this point, I don't see anything that's better than ice, but there have been some really crazy ideas. So as you may have heard, you know, we have several moons of large planets which have, you know, ice perhaps hundreds of kilometers thick on their surface. Enceladus is one that comes to mind. You know, there are Ganymede. Right. There are ice planets out there, and someday I could envision neutrino observatories consisting of satellites orbiting these ice planets using that incredible, low temperature cold ice as their observatory of the cosmos. Maybe seeing as much of the universe in neutrinos as we're now seeing it in optical. So, thinking outside the box there, the entire solar system is our playground in the future. I think that's probably the most exciting part of this for astrophysicists.
Yeah, you think about the other, like you said, there's 18 kinds of ice. I mean, the ice is fascinating. What if it was helium ice or methane ice or something like that, where you've got would that have a different, would that in any way change or improve the way you're able to do that? Plus, you're out in the cosmos, 800,000 miles away, wherever it is. It's pretty cool to be able to have a lab out there.
Yeah, that's right. I mean, this is the kind of thing that we can dream about in the future. If we can solve, many of the problems that we're facing as humanity, and be able to devote more of our resources to these kinds of things, then I think it may be that these are the futures that we can look for our children, our children's children, to be able to devote themselves to curiosity as a profession. What a wonderful world it would be if we solved hunger, we solved disease, and we're able to see that that we could follow these kinds of passions for what's true and what's not true about the universe. It would be wonderful.
Do you think it's become harder as time goes on to get funding for scientific projects? And on top of that, do you think that the way most people view science is, more friendly, more agreeable toward it? Whereas, like Carl Sagan said in a book once, there was this nerdy aspect to being a scientist. Do you think it's different now? Do you think people hold more respect for it?
Oh, I'm sure that the nerdy thing hasn't changed. I mean, just look at me, okay? So what I would say is that I think people greatly underestimate the ability of every American to get excited about some parts of science, and it may be different parts, but I never underestimate that. I think every time I have sort of one-on-ones with people that don't know what I'm working on, if I'm able to sort of to explain it clearly, I can see their excitement is there as much as anybody. So very often it's just the problem of us not explaining ourselves very clearly. As far as funding goes, yeah, I mean that has, I hate to say it, but in my whole professional career, which started as a professor in about 2000, it's been on a slow decline. And it's very troubling to me to see that. And I think especially for young scientists going into academics and research, the fact that this funding has been in decline for 20 years now is a real concern. I think we as a society we have a risk of losing our preeminence in science and in education if we don't somehow turn the corner on this. I think there are perfectly good reasons why this may be the case. It may just be that we're not doing as well as a nation, but I honestly don't think that's true. I mean, American ingenuity is just as good as it ever was. I think we can be as productive as a society as we ever were, and so I think we have to just find out, how do these priorities shift so that science, which has given us so much good in our society and has elevated us so greatly in the world, how did it somehow lose its priority with us? I think that's something we as a society need to recognize and change.
One of the things I talk about a lot, is like dealing, and partly because of my time at combat zones and looking at social problems, that they're really like cubed multivariate problems where it gets really impossible. You just put a pie there and go, I don't know what to do. Are scientific problems easier to solve, even if they're impossible? Like, things that are faster than light speed, there might be something out there, but it seems like social problems are they're damningly impossible to do. Is that as true for the hard sciences?
there are always problems which no one knows what to do about. An example in neutrinos is we know that the Big Bang didn't just produce microwaves, which are relatively easy to see now. In fact, we've been able to measure them to a gnat's eyelash. They also made neutrinos, and it made as many neutrinos as it did microwave photons. And that Big Bang soup of neutrinos is around us all the time. But nobody has thought in the 50 or 60 or 70 or 80 years, I can't even remember how long, we've been working on this problem of how to detect those neutrinos. No one can come up with a way. Their ideas have come and gone, and no one has been able to design an experiment yet that will detect those cosmic background neutrinos. So despite the fact that we have a theory and everyone believes it must be right, we still haven't measured them. So who knows? Maybe there's something weird going on there that we will discover if we can ever figure that out. So from an experimentalist point of view, that is one of the hardest problems in the neutrino world. In the world of theory, I think this finding unified theory with quantum gravity, unifying gravity with the other forces, that has just turned into such an incredibly hard problem. No one would have expected it to be so hard. And theorists have come and gone. And we still seem no closer to finding the answer to that than in any other part of physics. And there are some physicists now who claim that you can prove there is no answer to it. That somehow, it's one of those things which is a paradox wrapped in an enigma, and we'll never find our way around it. So yeah, I think those sort of two examples.
Yeah. Any final questions, Alex, at all? Or are you good?
Coming to the end of my college career here, at least for the time being, I've been trying to think of a project, and one thing I'm really interested in is, seeking life somewhere out in the universe. And one of the cool ideas that, I've heard from other people, and sort of what I wanted to talk about, is looking for signatures of life and atmospheres on, something that's very far away, like an exoplanet. Mm-hmm. But to bring it a little closer to home, in our search for life, do you think that there's still a chance that we could find it in our own solar system? And, if you were to lay down a bet, where in our solar system do you think we'd find it? Either current or past evidence?
That's a great question. That's one that I really don't have a good sense of. If we find life in this solar system, there's been, billions of years since, the first single cell organisms have developed on Earth. And it's possible that we may have seeded the solar system, and evolution will have created that life. We just don't know how hard it is to make life. Honestly, this is something that once you start trying to run the numbers, and I've even tried this myself as kind of a hobby, you start to see that the uncertainties in each generation of the math, they begin to grow exponentially. And at the end, you can say, well, the chances of life existing are either 0 or infinity.
Right. So, the Drake equation just keeps getting more and more complex. The numbers that result keep getting smaller and smaller.
It is a very difficult problem, and I don't think we have a handle on it yet. But what's exciting is in just the last 2 decades or so, we now know of so many exoplanets. This was unheard of when I was at your position in physics, when I was just finishing my undergraduate degree. No one was thinking at all about exoplanets, that was an unbelievable thing that happened. And the fact that we have so many of them, we have some Earth-like examples, I think this question is gonna the numbers are gonna change dramatically. Either we're gonna be able to tighten that Drake equation down drastically because we'll find nothing on these exoplanets, or we're going to find something, and that's going to be one of the most exciting moments in history for sure.
I love it. Hey, man, thanks for coming on. Hopefully we can
you so
have
much.
you on again the next time you got something to update or talk about,
Sure.
because we need more conversations like this that open up our minds and push us to think about things in a new way.
Thanks a lot, guys. I enjoyed immensely talking to you.
All right, I'm going to sign off. Stand by.